Hello, my name is Ravi Hadimani. I'm from Virginia Commonwealth University, and the title of my talk today is Effect of Cortex Coil Distance on Resting Motor Threshold in Schizophrenia Patient During Transcranial Magnetic Stimulation, or TMS. So this work is in collaboration with National Institute of Mental Health and Neurosciences in Bangalore, India, and Virginia Commonwealth University, School of College of Engineering, as well as School of Medicine. Emily is my student who did most of the work, and I am presenting on behalf of her. So, to begin with, I would like to first give the structure of my talk. So I will start with the motivation and introduction to TMS, and then I will talk a little bit about the latest development in TMS coil designs and how the coils can influence the TMS stimulation strengths or the treatment outcome. And then I will go to the development of anatomically accurate brain models using patient-specific MRIs. And then I'll talk about resting motor threshold, that is RMT, and how it is correlated to other TMS parameters. And then at the end, I'll talk about how the coil cortex distance, CCD, or it can also be called as brain scalp distance, that is the distance between the surface of your head to the surface of your brain, can affect your TMS treatment outcomes or other parameters. Okay. So the motivation for us to work in TMS or study TMS comes from various factors. One of them is the prevalence of neurological disorders in present days. In the US alone, National Institute of Health, NIH, estimates about 1 in 4 Americans above the age of 18 suffer from a diagnosable neurological disorders. That's a large number of people who suffer from neurological disorders. So there is a critical need for effective, non-invasive, and safe treatment for the brain disorders. There has been various funding initiatives by several federal agencies in the US, especially one initiative called BRAIN Initiative. BRAIN is full form for brain research through advancing innovative neurotechnologies. It's an initiative that funds across all the federal agencies for research in brain-related technologies. And similarly, there is another initiative in Europe called Europe Human Brain Project. The budgets for either US Brain Initiative or European Human Brain Project are in billions of dollars. So there is a large need, or there is a critical need for developing new technologies for treating brain disorders. We think that transcranial magnetic stimulation, TMS, or it is also often called as RTMS, is a promising technique that can treat various neurological disorders. It has become very popular in recent days. If you visit any major hospitals, you will invariably find TMS as a treatment for either depression or other disorders in psychiatry department or in neurology departments. So TMS is a neuromodulation technique that can alter brain function non-invasively, safely, and without the need of surgery or ionizing radiation. New TMS coils and procedures are difficult to test and validate due to the complexity of human brain. So although it's becoming popular, but there are several obstacles in developing effective treatment procedures. I will list some of them here. Those are because it is ethically difficult to study human subjects to test various TMS parameters. And also there is lack of brain phantoms, physical brain phantoms, and also lack of new improved TMS coils. Okay, so in this work, the motivation for this work was the brain scalp distance, that is BSD or CCD, can influence the treatment outcome significantly, because the magnetic field coming from a TMS coil will decay rapidly, and the distance between the coil and the brain is an important parameter because the field decays rapidly. So we need to study that distance and see how it is related to stimulation strengths and treatment outcomes, or the maximum E field that is induced in the brain. Okay, that is the motivation for our talk today. So briefly, what is TMS? So TMS is a technique where a transient or time-varying magnetic field will induce eddy current inside conducting parts of your brain by Faraday's law of induction. So that is del cross E is equal to minus dB by dt. So a time-varying magnetic field will induce an electric field in the conductive parts of the brain, that is the gray matter and white matter. So when this electric field crosses a certain threshold at the neuronal level, that is minus 55 millivolts at the membrane of an axon of a neuron, then a firing occurs in the neuron. And neurons also, they fire at their natural frequencies, but using TMS you can either upregulate them or downregulate them. You can initiate an action potential or you can suppress an action potential depending on how you apply the TMS. So it's a powerful technique which can be used to either initiate an action potential and start a neuronal firing that then propagates to other neurons. That's how the brain functions. So if you want to send a signal from a specific part of the brain to other parts of the brain, you can use TMS to do that. And by doing that, you can treat several neurological disorders. You can initiate activity in certain part of the brain and alleviate various symptoms as well. So this is how the TMS works. And because it is non-invasive, you can use a TMS coil on the surface of the head and initiate action potentials. It has a lot of potentials without side effects or risky procedures that are currently available, such as deep brain stimulator, wherein surgeons implant electrodes to treat Parkinson's disorder. So we can, if we successfully test TMS in phantoms and animal models, we could overcome the need for DBS surgeries, that is deep brain stimulation surgeries or treatments. So that is the potential of TMS. and that is one of our motivations. So what exactly happens? How do you generate a time-varying magnetic field? So basically, a TMS stimulator stores a large current in a capacitor and delivers to a TMS coil, and the coils are made of several number of windings, and depending on the number of windings and the amount of current you send to the coil, you can induce a high or low magnetic field. So because we need large magnetic fields in order to target target brain regions in the head, as the field decays rapidly. So we need a quite strong field of the order of 1 Tesla on the surface of the coil. So in order to generate so high field, we need large currents, and because we need large currents, the electrical components, that is a thyristor needed to control the triggering mechanism, they all become complex. So a stimulator is a well-designed stimulator is needed to produce a specific high magnetic field, specific in the sense a time-varying magnetic field with a frequency of 2.5 kilohertz. And we need 2.5 kilohertz because if we go any higher, the tissues won't respond beyond about 5 kilohertz. And if we go at lower frequencies, then our del cross E is minus dB by dt. So if your dB by dt, if your current is changing at a slower rate or slower time, then the resultant electric field will be small. So here is you see a magnetic field that is in the black line, and the corresponding electric field in the red line. They have a phase lag of about half a period, I think. So this is a sinusoidal wave. So this should be at a frequency of 2.5 kilohertz in order to apply a strong electric field. So as I said, we need high current. So a typical TMS stimulator that look like this in this image, they can go up to a current of 5000 amps at a frequency of 2.5 kilohertz. So the pulse duration is 0.4 millisecond, which is really small. So unless you stimulate for hours and hours, this won't heat up. And of course, we use copper coils whose resistance is quite low. Our impedance is we use lower we try to reduce impedance as much as possible, so the heating is minimized. Okay, so that is the signal frequency, but then the triggering, that is the pulsing rate, is about 10 hertz. That can be varied. It can go anywhere from 0.5 hertz to 50 hertz. Again, the repetition rate, higher the repetition rate, the quicker the coil heats up. So the established treatment for depression is it's FDA approved, and the parameters that are approved are 10 hertz repetition rate, and you have to treat a patient every day for 5 days a week for an hour. So 10 hertz for an hour, 5 days a week for about 2 months. This amount of treatment will leave a permanent physiological change in the brain. So for depression, it's the executive part of the brain which controls the emotion. So if you do so much treatment, it will permanently change the executive part and relieves depression, or relieves the symptoms of depression. So that is quite well studied, and there are a lot of reports on long-term studies and large number of patients, and fMRI reports that show how there is a permanent change. So some people, of course, it's very individual. The treatment outcomes are can vary from individual to individual. So some people might need some maintenance treatment. So the magnetic field coming out of the TMS coil depends on the shape of the coil and size of the coil. So this is how the TMS works. And it's as I said, it has a lot of advantages. And it has been FDA approved for treating depression, major depressive disorder, back in 2008. So there are 4 companies now that Neuronetics, MagStim, BrainSway, and MagVenture that produce these devices that are FDA approved. And it was also FDA approved for treating migraines in 2017. And recently, it's also FDA approved for obsessive compulsive disorder. And the companies that produce the stimulators or the devices for these treatment are BrainSway and eNeura. And there are a number of open label studies and clinical trials that are testing TMS for various neurological disorders. You name any neurological disorder, there is one or the other open study or clinical trial going on, or they might have reported already in the literature. Again, one of the drawbacks is of these studies is most of these studies use existing commercial equipment, which I will show why is not advisable to treat all sort of disorders with the existing commercial devices. So the advantages of this technique is non-invasive, and it can be done in an outpatient setting, and you can target a specific part of the brain. And it's currently with the existing coils, they're limited to cortex, or if they go deeper, then you don't have good focality. And then there is, whenever you produce a pulse, there is a clicking sound due to Lorentz forces in the coils, and coils can heat up if you stimulate for longer durations, longer than 2 hours. So these are some of the disadvantages. So a little bit about coil design. For a very long time, the 2 main coils that were quite frequently used in TMS are a single circular coil and a figure of 8 coil. So single circular coil, as you can see here, produces an electric field in the brain that doesn't have good focality. Along its rim or edges, it produces an electric field in the brain. The projection of that rim produces an electric field in the brain. This is not target specific, so this is not used for treatment procedures. However, a figure of 8 coil, because you add up the magnetic field here in the center of the coil, so you get a focal electric field in the stimulation area. So that is in the brain. And the commercial coils look like this. This is a modified figure-of-8 coil. And then the Brainsway uses an interesting type of coil, which is quite complex. But if you look at the shape of the coil, it ends up stimulating large area of brain. So that's how it is also called as deep brain stimulation TMS coil. That's because it has several coils that add up the magnetic field and can go deeper. But some of the cortical regions might get overstimulated, and it's hard to use this for focal stimulation. If you want to target a specific area in the deeper parts of the brain, it's not possible with Hesed coil or Brainsway coil. So we have developed new coils that can also go deeper. A first version of the coil called Halo coil was designed by Dr. Giles' group in Cardiff, and then when I joined his group in Iowa State University, we developed a triple halo coil which looks like this. Basically, it has three halo coils that come below the surface of the head, below the top of the head, and on the top of the head we place a figure-of-8 coil. So with this configuration, we can reduce the decay of the magnetic field coming from the top coil, and we don't overstimulate any of the regions. So here is what you can see. The deeper regions, for example, amygdala here, can be stimulated, keeping the top of the head at a stimulation strength, that is at a motor threshold strength. You can have the same strength here as that of a regular coil and still go deeper to regions like amygdala. And then we have developed another coil called quadruple butterfly coil that can stimulate cortical regions but with a higher focality. So these are a few different coils that me and my collaborators have developed for either treating or either stimulating deeper regions or stimulating cortical regions with high focality. So we have done a lot of simulations using heterogeneous head models, taking the MRIs of the patients and building head models. There is a lot of variation, and that comes to the current topic, that is the effect of anatomical features. One of them is the distance between the coil and the brain or the cortex. So that distance varies from patient to patient. So here we show that between different ages, the anatomical features are different, and hence we can't stimulate with the same procedure as we stimulate the adults. So what I mean is the normal treatment procedure is you establish a motor threshold. So you take the coil and start increasing the current until your thumb twitches, and that is your motor threshold, and that is an important parameter which I'll be talking a lot about. So that is called resting motor threshold, RMT, and that RMT depends on the distance between the coil and the brain. So, and this distance varies from people to people, and what clinicians, what they do is they determine this RMT, and then they go to other regions. For example, to treat depression, they get the RMT on the motor cortex, and then they come to executive part of the brain and using the RMT strength, they start stimulating the executive brain. That is incorrect, because the distance, the strength needed to initiate action potential for getting this motor twitch is different from from initiating action potentials at the executive part. So that's what we are trying to establish here. That is the relationship between the brain scalp distance and RMT. Okay, so in order to do that, we looked at several we looked at the data collected at different clinical TMS centers. And so one of them is Premier Psychiatry Research Institute in Nebraska, Lincoln, where they had treated 100 people. This just shows how the PHQ score, which is the degree of the disease, that is, higher the PHQ score, the more depressed is the person. So that shows how the PHQ score reduces when you treat over several sessions. So one of the interesting parameter we looked at is how the older patients were getting much better than the younger patients. And initially we thought this is because when people become old, brain shrinks by certain volume, and that increases the brain scalp distance. And when the brain scalp distance increases, the clinicians, when they determine the motor threshold, they need more current to get the motor threshold for older people. So when they need more current, so they get higher RMTs. So using higher RMTs, they end up treating the executive part of the brain. So that is, when they use higher RMT, they end up stimulating larger area with higher intensity. But they also go closer to the upper limit above which you can induce seizures. So because you use higher strength, you end up getting better results for older patients. However, we did not have these patients MRI images to determine the brain scalp distance. We only hypothesized that this may be due to because the older patients will have higher brain scalp distance or cortex coil distance. So we looked at models from Human Connectome project, wherein we looked at healthy young adults, and we saw a clear relationship between brain scalp distance and the maximum induced electric field on the motor cortex. And you can also see here that as the brain scalp distance increases, the percentage of volume being stimulated increases because you use higher RMTs. So that comes to the current study, wherein I think I'm running out of time. So wherein we collaborated with the National Institute of Mental Health and Neurosciences at Bangalore, where they recruited 20 schizophrenia patients, and for these patients we were able to get MRI as well as the TMS data. So the patient data were collected at NIMANS, and simulations and data analysis was done at VCU. So this is the methodology. So basically these are the 20 patients. You can see the variability in their brain structures, and here is our simulation where we show the induced electric field. So what we found, we also looked at the functional MRI, so which I'll talk soon. So what we found that in these patients there was no clear correlation between the age and the brain scalp distance, and also there was no correlation between the age and RMT. So this could be because these were schizophrenia patients, and they could the RMT depends very much on the brain status, or if the patients had coffee, or if the patients were not in a good mood, then that can influence RMT. We also looked at the maximum induced electric field and the age, and also the RMT and PANSS, which is nothing but the degree of disease progress in schizophrenia. So none of them had any clear correlation. So we thought that this might be due to because either the sample size is too small, or 20 patients is not enough, or there could be other factors that might be influencing the RMT values. So we verified our procedure again because we did not see any correlation. So we went back to our simulations and looked at a simple head model, and this is a standard anthropomorphic head model, which is homogeneous. It doesn't have any heterogeneity to it. We looked at just a homogeneous head model and looked at induced electric field and coil cortical distance, which has a clear correlation with R square close to 1. So that means our procedure is right. Just that the patients RMTs and the coil cortex distance was not correlated. That could be due to various factors. So we decided to look at the functional connectivity versus RMT. We had to take fMRI data from the patient for that, and then we had to run connectivity analysis, which is done at demands by our collaborators. So what we saw was the RMT had a negative correlation with the functional connectivity of two brain regions, which were associated with the schizophrenia. So these two regions, called as IC3 and IC4. These are the terms that are used for functional connectivity. They're called independent components. So these IC3 and IC4 connectivity, a good positive correlation, higher IC3 and IC4 value indicates a healthier brain. A smaller value indicates a non-healthier brain, or a schizophrenic brain. So when we looked at these IC3, IC4 connectivity data with RMT, we noticed that a negative correlation. So as the RMT increased, the functional connectivity value decreased. So that means there is a clear correlation with the functional parameter of the brain, which is IC3 and IC4. There are, of course, other connectivity parameters that you can look at, but this we thought was one of the important parameters with regards to schizophrenia. So that clearly shows that there is a correlation between RMT and the functional connectivity in the brain. So which means in order to determine the stimulation strength, we need to find correlation between RMT and the stimulation strength, which is a big challenge. We need to identify other parameters that influence this correlation between RMT and the coil cortex distance or the stimulation strength. So to conclude, To conclude, I would like to say that TMS is a non-invasive, safe, and surgery-free neuromodulation technique that can be used to treat several neurological disorders. And accurate modeling of TMS parameters and correlating clinical data is critically needed. And RMT is an important parameter in TMS treatment procedures that can influence treatment outcomes significantly. And in our study, we showed that the brain scalp distance or coil cortex distance and RMT are not correlated in our study. That could be due to various reasons. One of them is due to small sample size, which might have led to type 2, that is false negative error. Thank you. I would like to acknowledge my students and the funding agencies. My students have done a lot of work, not just in this study, but other studies that led to us completing this study. So I would like to thank my students and the funding agencies. If you have any questions, I would be happy to take, and here is my contact email. Thank you.